Okay, it's 11 o'clock. I guess we can get started. So today we are going to lecture 18, which is about air dispersion modeling. So this is my favorite part, and this is also my research. So I'm trying to make it a little bit fun, like more fun than other lectures. So first, we are going to talk about, so basically I want to introduce a model which is called Gaussian Plume model. But before talking about Gaussian Plume model, I would like to talk about how do the particles move in the air. And then we are going to derive a Gaussian Plume model by two approaches. The first approach is AD equation, which is a mathematical approach. And another approach is random walk, which is statistical approach. So we are going to use two approaches to derive Gaussian Plume model. And then we are going to talk about what is Gaussian Plume model. And then Gaussian Plume model is relatively simple. So it has some modified or complicated versions. So I would like to briefly talk about air mode. So this is based on Gaussian Plume model. And then we are going to discuss, like, can air mode be used for solving some of the problems? I put a star here because I'm not sure if the time is enough. So this would be the optional one. So now we can get started. So at first, I would like to talk about how do particles move in the air. And the first way of movement is called advection. So advection is the transport of a substance or quantity by bulk motion of a fluid, and it can be described by this equation. So basically, advection refers to, like, I have a particle here, and as the time goes, and this is a movement of the flow, we can say that as the time goes, the particle just moves along the direction of the fluid. And this is advection. And it can be described by, like, this is a flux, and this is a concentration, and the U here refers to the wind velocity. Note that the wind has its direction and magnitude, so it is a vector. Similarly, the flux is also a vector. Oh, this is not quite obvious. And this is advection. The next one is diffusion. So I think we usually mention diffusion, like, in terms of the water, and based on our daily experience, we know that if we add a dye into a solution, even though we did not mix it by our hands, we know that the dye will just disperse into the liquid, and finally it will be kind of like uniform in the whole space. Or we can understand this. So basically, the definition of diffusion refers to the net movement of anything, like the atoms, ions, molecules, or energy, from a region of higher concentration to a region of lower concentration. So basically, the driving force of diffusion is the concentration gradient. As long as we have the concentration gradient, there will be diffusion. But as long as the concentration gradient becomes zero, like it is uniform, then we do not have net diffusion. So similarly, diffusion can be understood as kind of like expansion. So as the time goes, like, the boundaries of the particles or the atoms, they just become larger and larger. But in the meanwhile, the average concentration in the whole space will decrease with time. And similarly, diffusion can be described in this equation. So in this equation, JD refers to the flux of diffusion, and again it has magnitude and direction. And K here is a function of space, and it's a diffusion coefficient, and it can be expressed as this. So you guys will not calculate the diffusion, so I just put it here to make it more more detailed. And C here refers to the concentration. So basically, concentration is a function of space and time. And this term, if we put them together, it represents the flux of diffusion according to the Fick's law. I guess you guys may learn Fick's law in Travis class, maybe. Have you guys talked about that? No? Okay, anyway, so basically Fick's law refers to, actually it refers to this. So it means that the concentration will diffuse from higher concentration, like the particles will diffuse from higher concentration to lower concentration automatically. And this equation, like we have this. So basically it shows the diffusion has this three-dimensional diffusion. It will just diffuse at any direction. So kind of like this. So for the advection and diffusion, do you guys have any questions? No? Okay. And then we can put these two movements together. So if we put them together, we can see that we have a particle that starts at time 0. And as the time goes, it will move with the flow. So it will have the advection. In the meanwhile, the particle will expand over time. So we also have diffusion. So the particle will be something like this. And this can be described mathematically. So basically, we can have the mass conservation equation. So this shows the concentration change over time. This term shows the net flux, and this term shows the source strength. And for the flux, it can be expressed as the contribution from advection plus the contribution from diffusion. And we already know that the contribution of advection and the diffusion, they can be expressed like this. So we can just plug them into the mass conservation equation, and we can have this equation. So this equation is called advection diffusion equation. And again, we can see that the concentration and the source, they are changing over time, and they may also change over the space. So they are the function of time and space. And for this one, do you guys have any questions? No? And I guess this is a little bit abstract. So we can see a real picture. So this shows the plume from a stalk. And in this picture, we can see that the wind, like something like we have the wind for this direction. And let's just say here. So we have the source. It will have some plume, which is relatively small. And then we can see it become larger and larger. So this represents the advection here. And in the meanwhile, we can see the plume become larger and larger. And this represents the diffusion term here. And the source refers to how much of the plumes or the particles from the stack. And this represents the source. So that this shows, visualize this equation. And the problem is we want to solve this equation, but we know that this is kind of like the differential, yes.
Why is it minus?
You mean here?
Yeah.
Oh, so this is plus. Oh, because this has a minus sign here.
Oh, I see.
Yeah, because for the diffusion, the concentration, like the default, is decreased. So so we want to solve this partial differential equation, and we know that it is a little bit hard to solve, like this whole thing. So to solve this equation, we may need to simplify it, and then we can have some additional assumptions to this equation to solve that. So let's just look at it one by one. For the first one, we can assume the emission rate is constant, which means the pollutant from the stack is constant. It will not change over time. And it is usually the case for most of the plant. So in this case, this can be evolved into this one. I'm not going to explain this equation in details, but we just need to know that the emission rate or the emission strength can be considered as a constant. The second assumption is wind velocity is uniform over the space. In this case, we can see that the wind, because it is uniform over the space, if we define an x direction, we can only describe the wind velocity in a scale value, and we can see the wind speed only change with time. And so basically it means that during the space, the wind has the same direction and the magnitudes of wind speed are the same. And the third one is diffusion is negligible compared with advection. So this refers to the fact that we know that if we have a molecule, like if it is in the wind, in this direction, and we know that because of diffusion, the particle may go to the direction that is opposite of the wind direction. In this case, we can consider this velocity is very small. So although we have the particle, because of diffusion, it will go to this direction, but because the advection or the wind speed is much larger than this speed, so in general, the particle will just follow the wind direction. Yes?
I missed it. Diffusion in the what is negligible?
Oh. So I think diffusion is negligible.
Okay.
Yeah. Yes, I guess there's a typo. And this can be expressed like this, but so in general, it means this direction can be ignored. And the fourth one is wind velocity and other meteorological parameters, like the temperature, relative humidity, are independent of time. It means that when we are doing the modeling, we can consider like the sun height will not change. And because of that, like the temperature or some other parameters will not change over time. And the fifth one is contaminant is reflected from the ground. So in this case, like if we have the ground, we have a particle, when it just goes to the ground, it will be reflected, fully reflected by the ground. It will not be absorbed or it will not precipitate. And so do you guys have more questions about the assumptions? No? And we also need some boundary conditions. So this is also a little bit overwhelming, but in general, it means that like if we have a source here, and let's say this is the x direction, we can see that at the upwind direction, the concentration of the pollutant should be 0. On the other hand, when we are go like very far away from the source, the concentration should also be 0 because it is very far away. So this describes like something like this. And we also, because we assume the pollutants will be reflected from the ground. In the other words, it means under the ground, the concentration of the pollutant should be 0, and it can be described by this equation. So you guys just need to just briefly know we have this assumption. You guys don't have to remember the math of that. And by having all of these assumptions, we can solve this equation. And the solution is like this. So I'm not going to show the process of how to solve that equation, but if you are interested, you can read this paper, and I think I put this paper as the reading material. So here is a solution of this equation, and we can see that if we remember the PDF, like the probability density equation of a Gaussian distribution, we know that I think this is 2 pi 1, and this is x minus mu and sigma square, and exp, like ex, oops, let me just rewrite it. So we have 2 pi and exp, and this is x minus mu. I'm not sure if we have a square here, maybe not, and the sigma square here. So for the normal distribution, we have something like this, and we can see that the formula, like the shape, the pattern of the solution is pretty similar to the normal distribution. We can say we have the exponential, and we have the z, which is a variable, minus the height, and also we have the standard deviation. So basically, this shows a normal distribution. And to apply this equation, we know that the Q refers to the emission rate, which we can measure it before experiment. And pi, we know its value. And x, y, z are the variables. And the height refers to the height of the source. So, like from the ground, we have the stack, and it will emit the pollutant. So, it refers to the height of the emission. Here, note that we have some space here because when the stack emits the pollutant, they have a vertical velocity. So when we do the modeling, we need to consider this height. So we usually use delta H to represent that. But we also have some variables that is unknown, like sigma y and sigma z. So these two variables are the standard deviation of the distribution concentration in y and z axis, and they can be expressed as this. So this is a little bit, I don't think this is interesting to solve, but in reality, we can use the empirical method to estimate sigma y and sigma z. So basically, we can do many experiments and have this empirical relations. So this refers to the x, the downwind distance. And in this case, if we know the x value, we can use this table to look up the sigma y value and the sigma z value. And you may also notice that we have this A, B, C, D, E, F. This number refers to the atmospherical instability. As we mentioned in the last lecture, we know that the temperature is decreasing over height. But in reality, like we have the temperature like this, or temperature similar to this. So different shape, like different real temperature, corresponds to different atmospherical instability. So we just need to know that under different situations, we can have different letters. So for this one, do you guys have questions? I think this is a little bit abstract, but we can see this picture, this graph, to show the Gaussian Plume model. So basically, it means that we have the releasing height from here, and because of the vertical velocity of the pollutant, it has an extra height here from the stack. And so this is a wind direction. We can see that along y-axis or along z-axis, it follows a normal distribution. So basically, it describes a 2D normal distribution. And we can also see that as the distance gets further away from the source, the sigma become larger. So the plume become fatter over the space. And this is making sense because when we are farther away from the source, the average concentration decreases. And so for this one, do you guys have any questions? No? And we can see that this process is a little bit not interesting. And when I first look at this process, I was like this. But when I was writing my PhD dissertation, I have to do the literature review. And because I use that model, I need to fully understand how it comes. So when I was preparing my PhD dissertation, I go through all that process. Okay, anyway, we know that this process is a little bit uninteresting. So we may also understand this process from another aspect, which is a random walk model. And I personally think this would be easier for us to understand. So basically, so this shows the work, but it is not random. So basically, we can assume we have the particle at t0, we have a particle, and let's just say this is 0, this is plus, maybe plus 10, this is minus 10. So for this particle, it starts at 0, and then for the next time, it will have a vertical shift or the vertical movement. And we can assume that this vertical movement follows a normal distribution. In other words, at t0, I'm here, but at t1, I can have a vertical movement, and the length of this vertical movement follows a normal distribution. And maybe at t2, I become here, and at t3, I'm here, and t4, I'm here. So basically, we can just move like this. So this is a random walk. And theoretically, we can show that, we can prove that. I'm not going to prove. But in general, if we take so this is T, if we capture all the particles here, we can prove that the particles, the number of particles follows a normal distribution. And if this is a little bit abstract, we can understand it like this. So we can just transform it into like the vertical one. And I guess you guys have already are familiar with this Gordon balls in a statistical class. Like if we have so many balls and if we just let them fall, we can see that the distribution of the balls will be like this. Do you guys remember what's this distribution? Because normal distribution? Any other Gaussian distribution? Yeah, I would say this is good. This is good because when we are talking about this, we want to relate this to normal distribution. But this is a binomial distribution, right? So this is a binomial distribution. And again, we have the table, like the map of distributions. If we look at clearly, we can see that for a binomial distribution, when the sample size or the number of particles become infinitely large, the binomial distribution will approach to normal distribution. And that's why I think when we see that, our first reaction is normal distribution. So basically, it follows a normal distribution. And because of the air pollutants, we have so many particles or the molecules. So the sample size or the N will be very large. So we can expect that to be a normal distribution. And here shows a simulation example. So here shows the one particle. It has the 100 steps. We can see the trace is something like this, like it is kind of random. But if we simulate 100 particles, and we can see that this shows some of the pattern. And we can see that if we take the sample here, if we take the cross-sectional area here, like if this is 0, we can see that this follows a normal distribution, like the number of the particles follows a normal distribution at here. Similarly, if we take the cross-sectional area here, and again, we can see the particles also follows a normal distribution. But this, we can see this normal distribution is flatter than that one. Do you guys feel cold? Shall we close the window? It's okay? Okay. And and we know that when particle flying in the air, because of the diffusion and some other like turbulence, this whole process is random. So we can assume the vertical movement of the particle follows a normal distribution. So we can have something like this. And this is also a little bit more abstract. So we can use this picture to demonstrate that. So if we have a plume, and if we take the picture, just instantaneous picture, we can see that the plume shape is like this. And because of the unknown, like the very random or chaotic turbulence, and the plume will be something like this. We can say the pattern is very random. But if we take many photos and then we overlap all the photos together, it will be something like this. And we can see this plume is very clear and very shaped. And so if we measure the concentration of the average, like if we calculate the average concentration of this cumulative plume, we can find that it follows a normal distribution. Similarly, if we measure the average concentration here, it will be something like this. So again, for this normal distribution, we already know that the mean of this normal distribution. But the standard deviation of this normal distribution, again, they can be found empirically by the same table. You have question? So for this one, do you guys have any question? No? And again, we can derive, like we can use the random walk model to derive this one. So again, along z-axis or y-axis, because of the random walk, the particles or the pollutants follows a normal distribution. So basically, it is a 2D normal distribution. And because when the distance gets further, the average concentration will decrease. So this normal distribution will become flatter. And like I personally think this approach is easier to understand than the previous one. So it will be something like this. So do you guys think which approach is better making sense for you guys? Or you guys may type in the chat.
Yeah, it's probably a little easier to like see.
It's more intuitive. Yeah.
I like the math better for the other one.
Yeah, the math, it makes sense, like from what I remember from calculus, which is not much. But it makes sense.
That makes sense. The math that AB equation makes more sense, but the visualization of the random wall.
I think that they both exist. Yeah. I think it's crazy that we can even like model that. Like, I never figured that, and we're so lucky it's like a normal distribution.
Yeah. And I think normal distribution just describes the nature. So I think this is the beautifulness of math, like including the math and statistics. And here I also want to show a point that I think when we are learning, like when we are having a class, I think sometimes like the professors or the instructors, they may use their own way to teach. So maybe their way does not quite making sense to you, or their teaching approach or their teaching material is a little bit hard to understand. So at that time, you may choose to talk to the professor, and that is always welcome. But on the other hand, another approach is that you may just go to the internet and search for the same knowledge. And sometimes you may find some other, I would say, unpopular or the other method that is not widely accepted. But that method may just make sense to you very well. So you may just try other methods to understand the same material if you get confused by some method. Okay, anyway, we have this Gaussian Plume model. And so what is Gaussian Plume model? It is a solution of advection and the diffusion equation. And when we are talking about the model, we need to talk about its assumptions. And for the assumption, I still use the assumption of the mathematical approach because that is more strict. Yeah. So they are the same when we are simplify this equation. And again, this model has some advantages, like it has simple output, or its form is relatively simple compared with other like fluid dynamic models. And it is computationally less intensive because it has already been simplified other than other fluid models. Also, it is relatively accurate. I put a star here because when we are talking about accuracy, or like the QA and QC, we know that different experiments or different research, they have different standards or requirements. So this may change case by case, but in most of the cases, the accuracy of the Gaussian Plume model satisfied with our requirements. And here shows an example of using Gaussian Plume model to predict like the zinc concentration from an industrial plate. And we can see we have 4 sources. So we can use the Gaussian Plume model to predict the concentration from each of the stack. And then we can just add them together. So for this one, do you guys have any questions? No? And then we know that these assumptions are very mathematical. For example, for the first one, the emission rate should be perfectly constant. But in reality, we know that the emission rates of anything will not be perfectly constant. So in engineering, we can just a little bit lose this assumption. For example, for the first one, we can see that the emission rate is relative constant. So it may have some fluctuations, but as long as the fluctuation is small, then we can use. And this is similar for the wind velocity. So the wind velocity is relatively uniform. For the third one, we need relatively large wind speed. And in this one, I would say they are the same. The fourth one, we assume the steady state. So steady state, as we mentioned before, it means the meteorological parameters are constant in a period of time. So they are independent of time. So in this case, we can see they are just need to be relative constant. And the force find the contaminant is fully or perfectly reflected from the ground. But in engineering, we know that when the particle hits the ground, it may be absorbed or precipitated. So in this case, we just assume the precipitation or the absorption from the ground is negligible. But as I mentioned here, we have one hidden assumption that I didn't talk explicitly. So do you guys want to guess what will be the last assumption during the whole process? Or you guys?
The property of the particle, though.
Excuse me?
Like the property of the particles, or like the size or the movement of the particles.
I think that. I think that makes sense. So we assume the particle has no mass, right? Yeah, I think we can also add this one. Yeah, particle has no mass, or the particle is light enough. Some other additional assumptions? So here I want to say the hidden assumption, like I want to emphasize, is this. Is a point source. So we assume the releasing point is just a point. So in other words, like in engineering, but we know that the source will not be very small as a point. So in engineering, we would say the size of source is small compared to the spatial scale of the transportation of the pollutant. And here I have another question. Bless you. For example, we have the lake or the wastewater treatment plant. We know that they will release like H2S. And if we are here, like relatively near the wastewater treatment plant, or on the other hand, we have the street, and on the street we have the cars, and the cars will emit NOx. And here we are by the street. So in this case, do you guys think can we use the Gaussian Plume model? Or you guys?
No, because if you're that close to something, then it's not behaving as a point source.
Mm-hmm.
But if you were really far away from it, then
Yes.
maybe. Also, thinking about it with the model, it wouldn't average. It's too close to the source for it to become a binomial distribution necessarily.
Yes.
And like for the cars, like that whole road, like it's not coming from one spot, it's coming from like a larger area.
Yes.
And
Yes.
I guess you could do the model like at each of those locations, but at that point there's
Yes.
other things you could choose.
Yes, that's a point. So I want to say that the answer would be yes and no. The reason why it is no because this is a point source, but absolutely they cannot be considered as a point. But the answer could also be yes, just as you mentioned, we can add them together. For example, if we have this area source, we can just make the integration of the x, y, z of the concentration. As long as we know the emission rate of each unit area, and then we can do the calculation. Similarly, for this road, we may consider it, or we may simplify it as a curve. So again, we can do the integration along this curve and then calculate the concentration. So it could be yes and no. And do you guys have any questions about this one? No? That's good. And the fourth one will be something about air mode. And we know that first, we start with the mass conservation model, which is small and relatively simple. And then we can evolve this to the Gaussian Plume model by adding some practical assumptions. Similarly, we can add some more practical assumptions to make the Gaussian Plume model evolve to have the air mode. So I put this picture because we have the small Pikachu, and it can evolve into regular Pikachu and can evolve into the larger Pikachu. And we know that as the Pikachu evolve, it will be stronger. Like usually it will be stronger, but we know that the speed will decrease. Okay, anyway. So what is air mode? The full name of air mode is American Meteorological Society Environmental Protection Agency regulatory model. So the keyword is regulatory model. So the government or the consultant company, they will use this model. So here is the full description of the air mode. I'm not going to read that, but we need to know that it is a steady state plume model. So it means the meteorological conditions will not change with time. And the general expression of air mode is something like this. And we have the F, which is a weighting factor, and we have CS and CC, which refers to the Gaussian plume. So we are already familiar with the Gaussian plume. So it refers to the Gaussian plume in the stable boundary and the Gaussian plume in the convective boundary. So for the stable boundary and the convective boundary, it is similar to what we have talked about in the previous lecture. So we know that this is T. If we have the temperature profile similar to that, this would be convective because the temperature is hot at the bottom, so we will have the convection. On the other hand, if we have the temperature profile like this, so the cold air at the bottom, hot water at the top, there is no convection. So in this case, the atmosphere is very stable. But we know that in reality, this state may change over time, and it could be the transitional or combination of these two different phases. So the air mode just takes the weighted average of these two states. And in the convective boundary layer, like when the temperature profile is like this, we have three Gaussian plume. The one is a direct source. So this could be kind of like the traditional Gaussian plume. But we also have the reflection from the boundary layer, like the top of the, like we know that the temperature will decrease here and it will increase here. So it will have the reflection from the top of this boundary layer. And we also have some of the pollutants, they may diffuse to here. And then we have a penetrated source. So basically, it considered three different sources. So it is a combination of three Gaussian plumes. So for this one, do you guys have questions? So we just need to know this is a combination of different Gaussian plumes. And also, we know that if we have the wind, if the wind just passes through a building, the wind on the back of the building will be different, like it will go down and it will just accumulate here. And also, like this study shows this effect. Like if we have a building here, and if we have the wind from this side, we know that at the back of the building, it will be something like the whirlwind at here. And this effect is called downwash and sidewash. So for the pollutant, we know that if we have the pollutant pass through a building, and if the wind velocity is something like this, then the pollutant will accumulate it, like kind of accumulate it at the lee side of the building or at the back of the building. So if we are here, we may have a very large exposure from the pollutant. So air modes include the influence of terror and buildings, and so it is more accurate compared with Gaussian plume model. And when it considers the effect, it uses the empirical approach. And so, in summary, air mode is a regulatory model, and we can find its information on the EPA website. And it is also a open source model. So on the EPA website, we can find, like this is a formulation, and we can find its original source code. I think that is in Fortran, which I do not understand. But it has some commercially available versions. For example, like the air mode view. At first, I would like to show a demo, but because of time, so maybe I can show that next time. And again, it inherits the assumptions of Gaussian Plume model. So because it uses Gaussian plumes, so at least it has the assumptions of the Gaussian Plume model. But it also has some additional assumptions when it considers the effects of building and terrace. Again, it has the same advantage of the Gaussian Plume model, but it may be a little bit more accurate than Gaussian Plume model. And because of the time, we're not going to the discussion, but here I just want to show the idea that by knowing the assumption of a model, we can determine if the model is applicable of a given situation. And I think this is the case for, like when we're applying for other models. At first, we need to evaluate its assumption and then compare the assumption of our situation. So I'm not going to do the discussion, but let's just look at this one case because I have a question, similar question in the quiz. Okay, so this question is, can it be used for modeling transport of pollutants from a large spatial scale, like from Europe to Asia? So for example, we have a plant here, it will have the emission of the pollutants. But like if I'm here, so can we use air mode to model the transportation of the pollutant from Europe to Asia? How do you guys think?
Technically, in theory, yes, but practically, no.
It's a lot of data of like terrain and wind direction and also time effects.
Yes. So the key is wind direction, because the wind will not be the same from Europe in this large area. And also, even though we have a constant speed, we know that because of the rotation of the Earth, it will just, I think, right-hand theory, I forgot, but it will be something like that. This one? Okay.
The westerlies go like that, and then once you get to Sub-Saharan, like right around Sub-Saharan Africa, then they start.
Yeah, like the Coriolis force, something like that. Yeah, anyway, so we cannot, and we can see it doesn't satisfy the first assumption. So we may just go through all of other assumptions to see if it is good. So I'm not going to talk about this one, so let's ask if we can simulate the pollutant from a stream, from the water phase, because the water is also a fluid. So you guys can think about it. And so that's it. Because of the time, I'm not going to go through this, but you guys can take a look. And finally, I want to emphasize that there's a little bit more. So for the next Tuesday, we will have the last lecture. I mean, this could be the last lecture, but the last lecture of the second last lecture, which is about data presentation. I would like to share some of my experience when we are presenting the data, because we will have the presentation in the independent study. And on Thursday of next week, we will have a brief introduction of the final project. So Maria is not available online, so we can watch her pre-recorded lecture together, and that will be about 10 minutes. And then I will try to answer some questions about the independent project, and also some final exam if you guys have. But here is the most important thing. At the Thursday next week, I will hand out the sampler during the lecture. So make sure each group or each squad has at least one student come to class here. So you guys can make a discussion, but at least one of you guys should come of each group. So I can give you guys the sampler, and I will give a brief introduction about how to use the sampler, because we are going to use that in the final project. And about the final exam, it will be the next Thursday before the Thanksgiving. And again, it will be 1 hour. And so the main content is about Unit 5, like the microbiology to air pollution. But you may use some of the knowledges from the previous unit. So that's it.